Welcome to episode 40 of the Yoga Meets Movement Science podcast. Before I explain what the topic of focus is for today's episode, I just want to give a little backstory to give a bit of perspective on why we're choosing to talk about this today. So, last summer in episode 22, we did an episode that was titled The Connection Between Strength Training and Range of Motion. And we had a very special guest on the podcast to talk with us about this. And it was the amazing and knowledgeable Greg Nuckols. And we were so excited to get to talk to him about that topic because he knows so much about the science behind strength training. So in that episode, Greg, and this is just the gist. We talked about quite a bit in that discussion, but kind of the gist of the connection between strength training and range of motion is that in general, if you strength train through like full range, quote, full ranges of motion, that research suggests that improves flexibility as effectively as stretching does. So that's kind of what the research tells us. And we thought that was a great topic to talk about on this podcast because a large portion of our audience are yoga practitioners. And so especially for yogis, that can be an encouraging message because as we know, like yoga involves flexibility. And sometimes there's a stereotype that strength training can make you, quote, tight or inflexible, or another term we sometimes hear is like muscle bound. That's like a story out there or a stereotype out there. But Greg basically told us all about the research and that strength training doesn't do that. In fact, it can improve flexibility and it could even be something that you do to improve flexibility. So anyway, that was a great episode. We definitely recommend listening to it if you haven't, but you don't need to have listened to it in order to listen to today's episode because today we have a different topic to focus on. And today's topic is basically we want to kind of flip around what we talked about last time, which was like, how does strength training affect range of motion or flexibility? We want to kind of flip the direction of the conversation and today talk about, can stretching make you strong? Or maybe more technically, can stretching make you stronger than like you are right now? So kind of changing, like flipping it around, flip the script, and that's our focus for today. And so we knew that in order to talk about this in like a very thorough manner, it would be really great to have the best of the best here to talk to us about this topic. So we're super excited to tell you that we have the amazing Greg Nuckols back to talk to us today. And we're just so happy to have him here. Greg is, this is the very first time that we are having a returning guest on our podcast. So he's our very first return guest. And let me, in case you are not familiar with Greg Nuckols, just want to give you a little lowdown on kind of what he's about. So Greg has his master's in exercise science and sport, or exercise and sport science. He's the co-founder of Stronger by Science. He's an international speaker. He's held 3 all-time world records in powerlifting. He's the author of multiple books, such as The Art and Science of Lifting. He's the co-creator of MacroFactor, which is the best nutrition app on the market. And he's the co-host of the Stronger by Science podcast, which is a podcast that we love. Greg is also a gourmet chef and a dog owner to Oswald, who's one of the cutest dogs. And just a couple other quick things to tell you about Greg before he starts coming on here is that
I think that's enough. I'm uncomfortable enough already.
You're so funny. Okay. Okay. Well, can you tell us about, we did talk about this in our last podcast, but can you tell us about how you're not a stranger to yoga, even with all of that like strength training and powerlifting connection?
Yeah. So I started doing yoga actually in high school. I had a back injury from sports and lifting. Um, and I forget who told me this. Maybe it was a physical therapist, maybe it was just someone in the gym, but someone suggested that maybe yoga could help with that. Um, and my senior year of high school, I didn't have a class first thing in the morning. And so 3 times a week, I would go and take a morning yoga class. That was the class was me and about 2 dozen women who were at least like 70 years old, um, which was just a blast. I think they enjoyed having a young person in the class. I was terrible at yoga, so it was good that I would not be getting judged by my peers, and it was a great time. Um, and then yeah, the thing that um, I told Jenni as a joke before the last time I came on the podcast is that uh, if one wanted to be as charitable as possible about my experience with yoga, you could accurately yet misleadingly describe me as a graduate level yoga instructor. When I was in grad school at UNC, um, they basically use the grad students to teach what they call LFIT courses, basically PE classes, um, and you get to say which classes you would prefer to teach, but there's classes that need to get filled. You don't always get your first choice. So I was assigned to teach a yoga class. Um, so yeah, I was a yoga instructor at the graduate level, during my time in college. I don't know that I was that good, but I learned as much as I could, and I did as well as I could. And yeah, that was fun.
I love that. Thank you for relaying that story. And I just think, yeah, that's very prestigious to be a yoga teacher at the graduate level. And, it just shows you're not a stranger to yoga. So, as much as you know about strength and strength science and all that, you also have some familiarity with like kind of what we do and what many people in our audience do, which is awesome.
I'll go ahead and mention the last thing that Jenni was going to mention when she was introducing you, which is
Oh,
just
thanks, Travis.
just to say that you do a really great job translating research for the everyday person and taking the broader context of what the body of literature says, and sort of contextualizing any one study within that. So it I mean, you demonstrated that for us on the podcast episode 22, but in all
Mhm.
of your work, you do an amazing job of that. And I think it'll be particularly helpful today because there are a couple of more recent studies that have come out on this topic that could, you could run away with the conclusion, or you could contextualize it within larger context of what this research body has said for decades, right?
Well, I think thanks, and I will certainly do my best.
Yeah, we'll see what happens. No pressure.
Yeah.
So to get us started, I think it's helpful to define terms and get everybody on the same page. And our audience is mostly yoga students and teachers, and so we're talking today, of course, about stretching, but also strengthening. And so, just colloquially, everybody understands what strength is, but if you could define that more from a technical term, both strength and hypertrophy, I think, and just like how we measure those things, or those things are measured in this area of research.
Sure. Yeah. So strength at its most basic level is uh, an assessment of muscle contractile force in some way, shape, or form. And how you assess it can look a variety of different ways. So the first strength assessments that probably come to people's mind are things like just one repetition maxes of just some sort of resistance exercise, like a bench press, for instance. It's going to test the maximal contractile abilities of your pecs, triceps, maybe anterior deltoids to some extent. Um, yeah, so you can assess strength that way. Um, you could look at just like maximal joint moments. So You could get someone in a knee extension dynamometer, really control everything super well, and look at just how many Newton meters of torque uh, of knee extension someone can produce, which tells you about the maximal contractile ability of the knee extensors, the quads. Um, you could try to even more directly assess contractile force than that by doing a bit of modeling, and not just looking at the external moment created, just in the output on the dynamometer, but you could look at like the internal moment arm for the quads to get an idea of just how much actual contractile force the quads are creating to create the joint moments that are observed. Um, and you can even get more basic than that by taking muscle biopsy, extracting individual muscle fibers, and rigging them up between the two just tiniest, most sensitive little force sensors you could possibly conceive of, and then electrically stimulating the fiber to like make it contract to look at the contractile force of just like an individual muscle fiber. Um, and I think you can get even more basic than that and analyze the force created by a single power stroke of like a myosin head. But
Oh my god,
that's getting like
what?
absurdly abstract. Um, but yeah, at the most basic level, strength is an assessment of skeletal muscle contractile force, which can be, you can assess it with anything from like very practical things like, hey, what's the heaviest thing I can pick up over my head, to very impractical but much more precise ways, like in a lab with a dynamometer and whatever else. So yeah.
And then just to compare or contrast that with hypertrophy, I think sometimes maybe people, well, I can speak from my own experience of when I was just getting into the field, I had no idea what that was or what the difference was between hypertrophy being muscle growth and muscle strength. I thought they were one and the same. So, like, how would you define hypertrophy in relation to strength?
Yeah. So I don't know. I'm sure I'll say hypertrophy multiple times over the course of this podcast. The more I think about it, the more I actually think I just prefer the more general term muscle growth.
Mm-hmm.
Um,
Mhm.
in part because that relays what you're saying to a non-academic audience easier. Like, you don't have to define terms. The definition is uh, kind of contained within the term itself. And on just kind of like a nerdier level, we like it's not okay. So hypertrophy refers to the increase in size of the muscle fibers you have, which then results in a increase in size of the entire muscle itself. That's contrasted with hyperplasia, which is an increase in the actual number of fibers within a muscle, which would also cause the muscle to grow. Um, and yeah, people refer to hypertrophy because the common understanding is that muscle growth in adult humans is like exclusively accomplished via hypertrophy, increase in size of the fibers you already have, rather than hyperplasia, adding new fibers. I actually don't think that that's as closed of a case as a lot of people think. I actually think hyperplasia like exists to a like meaningful degree, and we just haven't had like the correct studies to assess it. So anyway, I think that just the general term muscle growth doesn't just assume all of the growth we observe is due to hypertrophy rather than hyperplasia, but whatever. Yeah, basically hypertrophy is muscle growth, and you can assess that a variety of different ways. Oftentimes, it will be assessed indirectly. So, for example, if you go to a gym that maybe has like a 3D body scanner or one of the like BIA scales that you step on and it tries to tell you your body composition, um, don't put much stock in any of that stuff. Those are not great assessments of body composition, and body composition is only indirectly related to actual muscle growth. But what, like, it's kind of janky, but people will try to make inferences from that. Basically, like, hey, if you have some indication that you've put on 4 pounds of lean mass over the course of a training program, your bones probably aren't getting that much heavier. You're probably not adding that much organ mass. Like, a pretty good chunk of that lean mass you're adding is probably in the form of muscle growth. If you want to more directly assess it, um, then you're talking about just taking some sort of direct measure of muscle size. Outside of a lab setting, honestly, the
Mhm.
best you can do is probably just like limb circumferences. Break out a tape
Mhm.
measure, flex your arm. Is it bigger or smaller than it used to be? That's still like a pretty rough assessment. Like, there's some subcutaneous fat. You got the bone in there, but you are, in theory, like, your arm's probably not going to grow 3 inches unless you put some muscle on. Um, and then the ways to best assess it generally involve equipment that you'd only find in a lab. So you can look at the thickness of a muscle, or the cross sectional area of a muscle using an ultrasound device. If you have a bigger budget, you can look at the thickness or cross sectional area of a muscle using MRI, which basically does the same thing, but it's better,
Mhm.
but much more expensive. So it's not used as often. Um, and then if you want to look on kind of a microscopic level, much like with strength assessments, where you can look at the strength of an individual muscle fiber, you can take a biopsy, take a cross section of it, look at it under a very, very high powered microscope, and look at the cross sectional area of individual muscle fibers to see how that changes over time. Um, so yeah, those are most of the ways you could go about assessing hypertrophy or muscle growth more generally.
Thank you so much for such thorough descriptions of both of those two different terms and what they mean, especially in the context of this conversation. And I think just like understanding a bit more about like how they're measured also just helps give more of a concrete idea of kind
Mhm.
of what we're talking about. And also, I wanted to say, I think it's so awesome that you are kind of suggesting that maybe you're wanting to use that term muscle growth in place of hypertrophy, just in general or as some intention.
Mhm.
Because yeah, I know that at least I had always been taught that when muscles grow, it's because individual muscle fibers get bigger, but it's not because you increase the number of muscle fibers.
Mhm.
Like that was kind of this like big distinction that was made that I learned about. So I think it's really awesome and very interesting to know that, it seems like you're suggesting maybe we could also increase muscle growth, not just in muscle fibers getting bigger, but also maybe more muscle fibers.
Yeah, can I just mess up your outline real quick? Um,
100%.
so yeah, this podcast is about whether or the extent to which stretching could influence muscle growth. And I see one of the things you wanted to ask about is evidence from animal research,
Yeah.
which dovetails really nicely with the
Oh,
hypertrophy
yeah, yeah,
hyperplasia
yeah.
distinction.
Yeah, can you tell us
So
about that?
would you mind if we just jumped in there?
No, and actually, Greg, when we kinda, like, sent those questions to you, we were also like, "We don't have to go in any sort of" it's
Okay,
just like an organic, so just however
cool,
things
cool.
come up is great.
Yeah,
Yes.
so let's start there. This will be a good jumping off point for both the hypertrophy hyperplasia distinction and also the earliest indication that stretching might be able to result in muscle growth.
Yeah.
So in the mid 80s through the late 90s, there was a line of research started by Gagne and colleagues, if memory serves. Um, or no, Gagne was the one that observed the most hypertrophy. I think it was old Jose Antonio, the head of the ISSN, back when he was a PhD student. I think he did the first study on this actually. Whatever, those are the two names that will come up the most in this area of research. But basically, they were very long-term stretch studies, mostly in birds, though some other animals got into it as well, where essentially what they would do is they would get some birds and they would hang some weights on their wings, um, which would stretch the. I think birds have like two different kind of heads of the lats, the latissimus anterior and posterior. It's like putting that stretch on the wings would stretch the latissimus posterior, um, and yeah, just basically keep it in a loaded stretch all day, every day for weeks at a time. The early studies, it would basically just be like a lightweight, and hey, we're going to leave this on for a few weeks. Some of the subsequent studies applied progressive overload as well. Like, hey, we're
Mm.
going to do a lightweight for 2 weeks, heavier weight for 2 more weeks, even heavier weight for 2 more weeks, and observe what happens. But yeah, like no direct resistance training intervention, at least not the way
Mhm.
we would think of it. They weren't having these birds do reps. Um, I'm sure they probably maintained some degree of like isometric contraction, like against the
Mm.
load that was hanging off of them, but it was like primarily just a stretch intervention. And they observed a ton of muscle growth in those studies. Um, and notably, they observed both hypertrophy, so an increase in fiber size, and hyperplasia, an increase in
Mhm.
fiber number as well. Um, and the Gagne study, which observed the most muscle growth of any of them, it was. I mean, I don't remember the numbers right off the top of my head, but it was something just wacky, like a 300% increase in fiber
What?
size, and like I think like a 90% increase in the number of muscle fibers
It's
in these
crazy
birds'
sounding.
wings. Yeah, like they just got jacked. Um, but that leads to, so first, completely stretch based intervention observed a
Mhm.
ton of muscle growth, um, and also they observed both hypertrophy and hyperplasia, an increase in fiber size and fiber number.
Mhm.
um, and then subsequent research, some of it stretch research, some of it like resistance training research on a variety of other species, so not just birds but some mice, some cats. I think maybe there was a study on rabbits as well. um, like various interventions, some stretch interventions, some resistance training interventions, observing both hypertrophy and hyperplasia, increase in fiber size and fiber number. um, and so it seems like kind of in the animal kingdom, as muscles grow, you see both an increase in fiber size and fiber number. That seems to be a pretty generalizable thing. It got in people's minds, however, that in humans, the only way
Mhm.
muscles grow is via hypertrophy, not hyperplasia, because hyperplasia has never been directly observed in humans.
Mhm.
Um, and so now you might be wondering, well, Greg, you said you think the door is still open for hyperplasia. Why is that? And here's where we get into experimental methods. So you might be wondering, how were they able to observe hyperplasia in these animals? And it's they killed them. That's how they did it. Uh,
Right.
because
Right.
in an intact living organism, there's no way to count how many fibers someone has in a particular muscle, without like it's you have to kill the animal, and you have to actually take the full muscle, get a complete cross section, look down a microscope, and count
Oh my
one by
gosh.
one every single muscle fiber.
Oh my
At least that's
gosh.
what you had to do back in the day. I bet there's like an AI computer vision thing that can
Mm.
like identify individual muscle fibers and like automate that part of it now. But regardless, like you need to remove the muscle, take a full cross section of it, and just count every fiber. Um,
Wow.
which very time consuming stuff. And yeah, there's, for very understandable reasons, the old Declaration of Helsinki and whatnot. You can't run an experiment like that in humans.
Mhm.
Um,
Mhm.
so I kind of think the idea that hyperplasia doesn't occur in humans, I sort of think that's people conflating absence of evidence with evidence of absence. Um, because there's never been a study that has directly observed skeletal muscle hyperplasia in humans, but for very clear ethical reasons, you cannot design and run a study that would be able to observe hyperplasia in humans. Like you can't kill human test subjects. Um, or I mean, I guess you wouldn't have to kill them.
Amputate, maybe.
Yeah, you like amputate, like that
Oh.
theoretically could work. But again, like most people aren't going to be too excited about that prospect.
Mhm.
Um, so yeah, and also, I mean, it would be a lot more annoying to to do that, even if you could get ethical approval. Which, to be clear, I'm very glad you can't get ethical approval for that study. But even if you could, my God, it would be so much more annoying to do that study in humans than birds, because like we're talking little birds. Like their
Right, the
muscles
muscles.
got way bigger, but they're still very small in an absolute sense. So, you're counting a couple tens of thousands of muscle fibers.
Oh my
Humans
gosh.
have way bigger muscles than birds. Like if you did a quad training study in humans and looked to observe hyperplasia, you'd be counting hundreds of thousands or millions
Hundreds
of
of
muscle
thousands.
fibers. Like just the counting burden would increase by like a couple orders of magnitude.
And that's
um,
just in one subject too.
yeah. So yeah, I mean, my thing with hyperplasia is it has been observed in enough different animal species and with enough
Mhm.
different types of interventions, including like one of the ones in cats was like, I mean, it was like pretty chill. We're not talking this sort of like weighted stretch for multiple weeks type of deal. Like uh, they like rigged a cat up with sort of like a squat apparatus,
Oh my
um,
gosh.
and like induced it to do like little weighted squats. But like you can't get a cat to like train to failure and like push themselves as hard as you could a human. So like there's a resistance component, there was some progressive overload, but like we're not talking about a just crazy resistance training intervention. And they still observed both hypertrophy and hyperplasia. Um, so like yeah,
Wow.
I see no reason to suspect that hyperplasia
Mhm.
doesn't occur in humans as well. Um, and there is also like indirect evidence in humans. So there
There is?
was there was a cadaver study that looked at fiber number in the tibialis anteriors of people,
That's the muscle in the
where
front of the shin, just
yeah
in
yeah
case people don't know.
yeah. And so basically, if you like, especially if you play many sports, you tend to use your like weak side tibialis anterior more than your strong side. So like if you're like a righty and you're
Mhm.
right foot dominant and you're playing soccer, like you're always planting on your left foot to
Oh,
kick
yeah.
something, like that has to be stable.
Oh, yeah.
Um, and so like over the course of a lifetime, you probably use your non-dominant side tibialis anterior a little bit more than your dominant side tibialis anterior. And there was a cadaver study where they like took the tibialis anteriors of cadavers, um, and like for people who they knew if they were righties or lefties, and their non-dominant side tibialis anteriors had more muscle fibers than their dominant side. And like that's cross sectional research. They didn't take that measurement before an intervention, run an
Mm.
intervention, test
Mhm.
again afterwards. So like you can't necessarily assess causality there, but it does seem unlikely that for whatever reason, like your body during fetal development would know which side would be your dominant side and just know to put more muscle fibers in the tibialis anterior of the
Right.
non-dominant side. Like I can't I can't believe that that would be something that would be impactful enough to exert enough evolutionary pressure for that to be like selected for in the gene pool to yeah. So uh, I mean that is indirect evidence, but I think it's like reasonably strong indirect evidence.
Yeah.
Um, and yeah, so I suspect that I strongly suspect that hyperplasia occurs in humans as well. Which is why as time goes by, I just prefer the term muscle growth instead of
Yeah,
hypertrophy, because I do think just counting all muscle growth as hypertrophy is like tacitly assuming that hyperplasia doesn't exist, and I think it
totally.
does.
Do you have a sense from those animal studies like what the percentage of the one versus the other is? And like does it even matter?
Yeah, in all of the studies, hypertrophy was the kind of predominant
Mm,
mechanism of muscle
mhm,
growth. Like I said, in the Gagne like progressive overload bird stretching study, you saw like a in excess of 300% increase in fiber size and a near doubling in fiber number. So, I mean, doubling in fiber number is nothing to shake a stick at, or nothing to sneeze at. But yeah, I mean, the change in fiber size was 3 times greater. So yeah, I do think, and that like carried through to all of the studies, like all of the studies that did observe both hypertrophy and hyperplasia, the like relative increase
mhm,
in fiber size was larger than the relative increase in fiber number. So I do think that hypertrophy is still the kind of like predominant way that
mhm,
muscles grow, but
mhm.
yeah, I mean, I think hyperplasia is a thing as well. Another great
So
example of
cool.
this is there was a study by McDougall and colleagues, I think from like '82, um, which there are like two cool things in this study. It was a study that a lot of people, myself included, cite when talking about sarcoplasmic hypertrophy. That's another like big rabbit
Oh,
hole.
yeah, yeah.
Um, people thought sarcoplasmic hypertrophy was a myth for a long time. More data is suggesting it's real, but people were like there was really no data to support it until recently. But study by McDougall in the '80s
Uh,
was like pretty suggestive that that sarcoplasmic hypertrophy was occurring. Not going to go down that rabbit
yeah,
hole.
yeah.
If you wanted to do a podcast on sarcoplasmic hypertrophy at some point in the future, I'd be happy to come back on. But
That would be awesome.
that would get us way off course for this.
Yeah.
Um, anyway, but that same study also is, I think, like indirectly suggestive of hyperplasia in humans as well. So basically there were two groups of subjects. There was an untrained group of subjects, and there was a group of subjects composed of like competitive powerlifters and bodybuilders. So people who were like quite strong, quite muscular, had been training for a long time. Um, and they put them on, I think it was like a 6 month training intervention. Like it was a pretty long training intervention, but again, we're talking months, not years. And they took muscle biopsies pre and post, and looked at fiber size and also like the constituents of muscle fibers, and that's where the sarcoplasmic hypertrophy stuff comes in. But one of the bit of indirect evidence that relates to hyperplasia is after 6 months of training, the initially untrained individual's muscle fibers were not statistically different in size from the powerlifters and bodybuilders who'd been training for like 10, 20 years,
Mm.
whatever, um, which suggests one of a couple of things. Um, Either uh, you only have 6 months of growth in you, and past
Yeah.
that
It
point,
just
no
stops.
more hypertrophy. Yeah, you've topped it out. Your fibers are as big as they're going to get.
That's great news.
Um, I think there's, I don't know, that conflicts with every observation any strength coach has ever had in their entire life. Uh, Another possibility is just that people who like take to strength and physique sports maybe start with way smaller muscle fibers than everyone else, and
Hmm.
therefore when they start training they just have more room for those fibers to grow, and that allows their muscles to wind up getting bigger. That's a possibility, but I think it's relatively unlikely. um, like there have been a few studies looking at whether like initial muscle fiber size is predictive of responsiveness to training, and it doesn't really seem to be. Um, and then the final possibility is that, yeah, I mean, you can experience quite a bit of skeletal muscle hypertrophy, and then past a point to keep growing, maybe around the time growth and gains really start slowing down, maybe that's when hyperplasia starts kind of
Right.
kicking in and potentially taking over as a more kind of like key mechanism for ongoing growth. And that's the interpretation I personally favor. Anyway, we can get back to stretching, but yeah, the stretching research in animals observed muscle growth, which consisted of both hypertrophy and hyperplasia. And I suspect both hypertrophy and hyperplasia occur in humans as well, which is to say, I like the more general term muscle growth.
Yeah.
I think it's both simpler and more accurate.
Yeah, potentially more inclusive or not like presuming just like
Hmm.
one type. That's super helpful and really you're like the first person that I've heard really make that case and so convincingly. Like it's just thank you for sharing that. I think it's super interesting when we're learning and talking about muscle growth. It's yeah, helpful to think about the different possible ways that it could happen and that, maybe something different can take place in humans than we've traditionally been taught or
Hmm.
what the textbooks say. And that's super cool. So I guess along the lines of I'm gonna try to reprogram myself from not saying hypertrophy to just saying muscle growth. This is gonna take a little while. But along the lines of muscle growth,
Hmm.
we thought just kind of, because we're talking about stretching and its potential connection and contribution to muscle growth, but of course also strength training as well. It seems like it would be helpful if you could outline for us just some ideas about the mechanisms for muscle growth, for how that happens. I have learned from you that I think that that's really like a far from settled issue in the
Hmm.
scientific literature, and you tend to hear different things out there. Some people really say it's all about just this one thing, and some people say it's all these things.
Hmm.
Could you just like maybe give us a little overview of how muscles grow, like what causes them to grow, and then that can help us thinking about stretching.
Your elevator pitch for the mechanisms of hyper or muscle growth.
Yeah. Man, I think that this is I think that it's a much more open question than a lot of people think.
Hmm.
But yeah, here's kind of as briefly as I can do it. Um, in I think like 2010,
Yeah.
Brad Schoenfeld published a paper where he proposed that there were three primary mechanisms of muscle growth: mechanical tension on muscle fibers, um, metabolic stress, and muscle damage, and that those were kind of
Hmm.
like the three key things that ultimately resulted in muscle growth. Since then, the balance of evidence has kind of shifted towards damage and metabolic stress probably not being all that important. Um, I don't know how much to go into an explanation of like how that consensus was reached. Whatever, like that's sort of that's sort of where things stand today. Yeah, just to give two quick examples.
Yeah.
So let's see the it was previously assumed that uh, so there have been a decent number of studies showing that like heavier and lighter training, as long as you go to muscular failure or pretty close to it, seems to result in pretty similar muscle growth over
Hmm.
time. And people looked at that and said, well, tension on the muscle seems like it would be lower with low load training. Tension seems pretty important. Growth is still pretty similar, but there's quite a bit more metabolic stress. We see more just metabolic byproducts being produced with low load training. So, maybe that is something that's contributing to muscle growth.
Mm.
Also, like blood flow restriction training, that kind of increases the concentration of uh, like metabolic byproducts in the muscle. That seems to be pretty effective for muscle growth. So,
Should we define that real quick? Blood
I
flow
don't.
Blood
restriction
flow
training.
restriction.
Oh, sure. So, um, you, you would mostly do it for your arms and legs, and if you have access to the cool equipment, it's basically like an automated pressure cuff that um, can like tell when it has cut off venous blood flow but still allows arterial blood flow in. So like you can get blood into the muscles, you can't get blood out of the muscles.
Oh.
So allowing oxygenated blood to get in still allows um, normal energy production to take place, still allows you to perform, but all of the metabolic byproducts that result from muscle contraction and burning through a bunch of energy, they can't get out because you've
Right.
cut off venous blood flow, like to return all of that like back to central circulation, back to your heart, etc. Um, so yeah, that should like increase metabolic stress. If you don't have access to one of those automated pressure cuffs, the way most people would do it in the gym is you just get a knee wrap
Oh.
and put it like either kind of in your armpit or like as close to your groin as you can get it. And the the kind of practical test you can use to see whether it's doing what it's supposed to is if you're not cutting off if you're doing what you're supposed to, you're allowing arterial flow in, you're not letting venous flow out, you get the best pump you've ever experienced in your life. Just a skin splitting muscle pump. It's awesome. Um, if it's too loose,
Mhm.
then you can still get venous return, blood still getting out. It just feels like a normal set. You don't
Mhm.
get that kind of like magnified pump. And if you get it too tight, um, I mean, it feels like a tourniquet. Like your
Mm.
lymph starts turning purple. You don't get a great pump because you're not getting more blood in.
Right.
Performance is terrible. Like you fatigue really quickly because you can't get oxygen to the muscles. So yeah, you can it doesn't take that long to get a pretty good feel for how tight the wraps need to be.
Don't they
Mhm.
say
And
like a
you,
7 out of 10 tightness or something? I mean, I know that's subjective, and maybe I just
yeah,
made that up.
no, that is, yeah, that is what they say. But I mean, that's going to depend pretty heavily on what your like
Yeah.
individual kind of like pain or
Mhm.
discomfort
Hmm.
threshold is. But yeah, basically, if you do it with a knee wrap and you get a ridiculous pump, you did it right. Um, anyway, so those are kind of like the lines of evidence that people would point to suggest that metabolic stress was pretty important.
Mhm.
Um, but what so then like people got to kind of understand individual fiber behavior a little bit better. So like you are producing less total force when you're lifting a lighter weight than a heavier weight. So kind of the total tension within the muscle will be lower. Um, but just due to how like individual motor units kind of come in and drop out like over the course of a fatiguing set, it does seem like each individual fiber is probably still exposed to a very high level of tension if you take a light set to failure, which sort of suggested that like, oh, maybe we don't need a non-tension explanation for why low load
Mm.
training is pretty effective for muscle growth. um, and then there were also a couple I think really cool, um, like from a study design perspective, a couple really cool studies that I think isolated the variable of metabolic stress quite well, where instead of doing blood flow restriction during a set, essentially what they did is one group would train just like doing normal sets, whatever. The other group would train just doing normal sets, but then instead of recovering like normal, they would put a blood flow restriction cuff like on their arm or leg when the set ended. So you're not
Mhm.
causing additional metabolic stress during the set, but you're basically like making the muscles marinate in that metabolic stress for longer than they would have otherwise. So like so that's a experimental design that allows you to equate load, tension, allows you to equate volume, but basically gives one group a greater like area under the curve for exposure to metabolic stress. And if that was like an independent causal mechanism for hypertrophy, that should have resulted in more muscle growth, but it
Very
Mhm.
didn't.
cool.
Um, so
Mm.
yeah, that kind of got people thinking, maybe metabolic stress isn't all that important. Um, with muscle damage,
Mhm.
that I think the the basis of the idea, I think a lot of it just kind of came from lore. Um, where I mean, like bodybuilders have been saying for a long time, like, oh yeah, if you're sore after a workout, that means like you really
Right.
trained the muscle good, it was effective. And it is also like it's difficult to disambiguate um, tension and muscle damage because generally, like tension is what's causing muscle damage. Like you're
Right.
putting higher forces on these tissues than they're accustomed to. That causes little micro trauma, muscle damage. So yeah, it's hard to disambiguate those two things. But just based on kind of like timing of stuff, there were some suggestions that muscle damage was pretty important. So if you're completely untrained, completely naive to training, you experience more muscle damage and muscle soreness after exercise than someone who's been
Mhm.
doing a particular style of training for months and months or years and years. Um, and that early training period is also generally where you experience the most muscle growth. So the period of like greatest muscle growth also tended to coincide with the period of like greatest muscle damage. So, since those two things occurred together, that suggested, like maybe this is
Mhm.
important. Um, but then a few years later, we find out that and I think this is just like a cool little fun fact that you can use if there's like a friend or someone in your family who's maybe interested in starting to exercise but like doesn't want to get super sore. Turns
Mhm.
out you can mitigate, like you can just significantly mitigate muscle damage and muscle soreness by just doing really easy exercise for like a week or two before you ramp it up. And like it's almost
Ooh.
comical how easy the exercise can be. So these studies, it'll basically be like if you take someone who's completely untrained and just have them do like 3 sets of 8 to 10 bicep curls to failure, their biceps will be super super sore the next day.
Mhm. Mhm.
If you put them through just like 2 weeks of training, that's just like you get a rough idea of how strong their biceps are, or just guess and just use a really light weight. Like what the studies do is like they look at maximal isometric force and then they use a load that's approximately 20% of that. But like 20%, we're talking very light, something you could probably do for like 50 to 100 reps,
Wow. Wow.
and just do like the same 3 sets of 10 with like 20% of
What?
1 RM for like 1 to 3 weeks. And that cuts down on the muscle damage people experience and the soreness they experience from their first like hard workout by like 80-90%. Like
That's
it doesn't
crazy.
it doesn't entirely make sense to me, but like
And that's objective too. That's not just subjective. Like they're measuring some sort of marker of muscle damage.
oh man, I would need to dig into those
Yeah.
studies again. I'm pretty like I know they
Subjectively is obviously the important part to
I
like the person.
yeah, I know they report soreness. I'm reasonably confident they report like CK as well. Um,
What's CK?
or
Creatine kinase.
Oh,
yeah,
oh, okay.
creatine kinase. Sorry.
Yeah.
Um,
I got lucky.
yeah. Uh, but yeah, like so that like with just a very little bit of initial loading, you can cut down on the amount of uh, like soreness and muscle damage people experience dramatically.
It's
And
remarkable.
so yeah, I mean, like it seems like it shouldn't work, but like it very
That's right.
reliably does.
It's
Like
so far from failure or whatever. It was just
yeah, like 1 or 2 very easy sessions with the same exercises you're going to train pretty hard.
yeah.
It is really all it takes. But anyway, so
That's a great trick
then
to know to tell someone.
yeah, so some enterprising researchers looked at that and said, oh, well, we can use this to determine if muscle damage is actually causative. Like we're going to put two groups of people in the
Right.
same program. One group of people, they're going to just get into it whole hog from day one. The other
Mhm.
group of people, we're going to give them 2 or 3 introductory weeks of like really easy exercise with the same type of stuff that they're going to be training hard later. And then when they start training, they're not going to experience much, if any, muscle damage, which like they took measures to verify that. And so yeah, they figured out a way to like experimentally like equate training, but
Yeah.
like assign muscle damage to one group and very
Yeah.
little muscle damage to the other. And they observed the same muscle growth in both groups, which suggests that like
Wow.
that muscle damage probably isn't a like primary driver of growth. So as all of that was occurring, there was also a lot more like molecular work being done
Mhm.
to better understand how how your muscles like feel what's going on around them,
Mm.
basically. And that provided like further evidence that like tension is very important. Essentially, like your muscle fibers are hooked to the connective tissue that goes around and all through your muscles and eventually becomes your tendons. Like people think about muscles and tendons as like two separate structures.
They
Your
do,
tendons
yeah.
are your tendons are part of your muscle. Like all of that collagen that eventually just comes together as a single tendon didn't come from nowhere. Like your endomysium, perimysium, epimysium, like in and around your muscle fibers and fascicles and the whole muscle itself, that just all comes together, and where the muscle fibers end and that connective tissue continues, like that's your tendon. um,
So
Same thing with
cool.
bones, actually. Tendons and bones, same thing. Like they're continuous. People think about. I know I'm getting off topic, but
It's
what
good
I think
No,
stuff.
this is
this is
cool.
super it's super fascinating, and yeah, our audience loves this kind of
when
stuff.
when people think about bones, they think about like the mineral part, like the calcium phosphate that you know it's what makes your bones hard, like the white stuff that yeah gives you hard bones. But like um I think like your bones by mass. I'm gonna get myself in trouble because I don't remember these exact quantity. But basically, your bones, the non-water portion is like basically 50% mineral and like 50% protein, and the protein is the collagen that is your tendon.
Oh,
Basically,
the
like
same material.
yeah, like it's not like it's not like your tendon comes in and it's just like collagen that is glued to
Right.
the
Like
the
adhered or
minerals
something.
of your bones. It's like you have the same type of collagen that composes the connective tissue in your muscles that becomes your tendon is also in your bones. And like your tendons don't aren't like glued to your bone. They're just continuous with that
Right.
collagen that is in and around your bones as well. So yeah, it's like a fully like integrated thing, like very like just completely stitched together instead of like these like completely separate tissues. um Dang, where was I going with this?
About tension? Like mechanical
Hmm.
tension and
Yeah. So yeah, I got distracted talking about tendons.
the
Anyways,
continuity.
yes. So the connective tissue in your muscles that eventually becomes your tendons, um there needs to like that they're ultimately what is transmitting force from your muscles to your bones, and then that creates joint torques, that creates movement, etc. So your muscle fibers are basically hooked to the endomysium, the connective tissue that surrounds them, um, at like what are called like focal adhesions.
Mhm.
And there's a protein called focal adhesion kinase that is basically like there where the like connective tissue attaches to the muscle, where like that force can be transmitted. And when like shearing force is put on that protein complex, um, so it's called focal adhesion kinase. What kinase means, if someone listening to this has taken biochemistry, is basically that means that part of the protein just like gives a phosphate to something, which just kicks off a big series of reactions within your muscle that basically that focal adhesion kinase, it when it gives a phosphate to a nearby protein, that is it telling the nearby protein, hey, this muscle is currently under tension. And then just like the downstream signaling effect of that one little handoff of a phosphate is the signaling pathway that ultimately results in upregulation of protein synthesis and ultimately muscle growth. And there are a lot of like different redundant pathways that can get you to that upregulation in muscle protein synthesis. But like that seems to be a very key and important one. And like on a basic level, like it causally links mechanical tension with
Hmm.
the process that ultimately results in muscle growth, which is like a clear, just kind of like one-to-one connection that you can't really draw with any of the other proposed mechanisms of hypertrophy, like metabolic stress or muscle damage. So that's where things are at today. With I think that people are maybe getting what I would term a bit too like tension reductionistic, where now it's gotten to the point where it seems like it is at minimum way more important than metabolic stress and muscle damage. Um, but I think there are also like other potential like mechanisms of hypertrophy that just haven't been
Mm.
adequately explored yet. Like
Hmm.
basically if like us knowing tension is causal does not necessarily imply that there aren't other causal mechanisms out there.
Right.
And I also think that people do get like a bit too reductionistic about it, because like there are predictions you could draw from like in understanding that tension is all that matters,
Right.
um, that aren't borne out in the research. So like for instance, if tension is all that matters, there should be very few training interventions that are more effective than just like a maximal isometric contraction, because like that's going to create more tension than a concentric contraction.
Mm.
And since you can create a stronger isometric contraction than a concentric contraction, and since load, like the loads you can use are going to be limited by what you can lift concentrically, you're
Oh, yeah.
practically your muscles can create more eccentric force than isometric force. But
Right.
since the loads you can lift during normal training are going to be limited by concentric strength, which is less than isometric strength, the eccentric force you experience is probably going to be less than like the total tension of a maximal isometric contraction. So basically, like yeah, like just flexing your muscles really hard against an immovable load would theoretically be like the
The
best
best
hypertrophy
way.
training. Or
Yeah.
I mean just like super maximal eccentrics would also be like incredibly good. But like there's research on those things, and like yeah, they result in muscle growth, but like they don't seem that special.
Mm.
Like they don't seem to be better than just kind of like normal resistance training, which is lower tension. So I, I
Mm.
don't I don't think tension is all there is, but
Uh-huh.
I do think of the mechanisms that have been uh, explored and studied in a fair bit of depth. It is the one that does seem to be the most important.
That makes a lot of sense. Thank you so much for explaining that so clearly. Um, when we're talking about mechanical tension or tension,
Mhm.
there's a difference between active tension and passive tension. Is that
Mhm.
right? Could you,
Yes.
because I think that that is relevant for thinking about stretching and really all
Mhm.
this, but could you explain the difference and like why it matters active versus passive tension?
Sure. So active tension is within all of your muscle fibers. You have these structures called sarcomeres, and within
Hmm.
your sarcomeres, you have these proteins called actin and myosin. And you can think of actin as a rope, and you can think of myosin as like if you've ever watched a strongman competition, and they kind of have like the hand over hand rope pull where you are like sitting down and you pull like a tire closer to you hand over hand. That's basically what
Cool.
myosin does, but it has like a bunch of hands. It's like a strongman octopus doing
Oh my
the tire pull. Um,
Pulling the rope.
Yeah, like there are sites on actin where these heads on myosin can attach to, and as you're cycling through ATP, yeah, like basically one head will grab onto a piece of actin, and then it will, like, the shape of the protein will change, which kind of like pulls the myosin along the actin, and then it releases, and then it grabs onto the next piece, and
Mm.
and you just repeat that as if you have a rope, but then you also have a rope parallel to it that has a bunch of hands on it, and they're all pulling. Um,
That's a great
and yeah,
visual.
that's how muscles contract on the most basic level. So that's anything that results in that is active tension. Um, and that can take the shape of a concentric contraction where those little hands are successfully pulling the tire closer to themselves. That can take the place of an isometric contraction where all of those little hands are holding on to the rope for dear life, but they can't quite pull it closer to themselves. The rope is pulling away with about the same amount of force, so you don't get a change in muscle length, but it is still like an active process. And that can take place eccentrically as well, where the rope is just pulling harder than the hands can manage, and it's slowly getting pulled away from them, but they're still holding on for dear life and kind of going hand over hand backwards the other way. Um, and all of those are active processes that involve those interactions between actin and myosin to produce active tension within the muscle. Passive tension, on the other hand, it's basically tension developed any other way. And there are two primary ways it comes about. One is, as I mentioned before, um, all of that connective tissue in your muscle is
Mm.
also continuous with your tendons. As we all know, tendons can store like passive elastic energy, like that helps with movement economy, with running. It helps you jump higher. Um, when like the collagen in those structures is resistant to a change in length, but when enough force is put on them, they will stretch a little bit. Um, and yeah, they provide resistance to that stretching, that change in length, and yeah, that's passive tension. There are also other proteins within the muscle fibers themselves that um, resist each individual sarcomere stretching too far. The most important is the protein titin, Titin, not Titan. But
Like a
if you said
giant.
AN, it would still, yeah. If you said Titan with an A to imply a giant thing, it would still be close enough to correct, as it is the largest protein in the human body. Uh,
Ooh.
just a fun little piece of trivia. But yeah, if especially when the muscle is actively contracting, if
Hmm.
it continues stretching too far, like titin, which kind of runs sarcomere to sarcomere, will kind of like lock it down and try to resist a further increase in sarcomere length, and that adds passive tension as well. And yeah, I think that the concept of passive tension is pretty easy to understand on a conceptual level, unless you're just incredibly flexible. If you bend over and try to touch your toes, at some point before your head is between your knees, you'll probably feel a stretch in your hamstrings. And to keep going down, you have to like actively pull yourself down, or someone would
Oh,
like need
yeah.
to push you down further. Well, that's force being required to cause a further change in length, and that's passive tension within the muscle resisting that.
Hmm.
Huh, yeah,
So yeah,
yeah.
those are the uh, yeah, that's what I got on active versus passive.
Thank you for that. So, would it be sort of correct to think about it in terms of like active tension is the result of an active muscle contraction as directed by the nervous system or as initiated by like the nervous system? Like
Mhm.
that's the act, like the nervous system signaling and causing that contraction to happen, whether it's isometric or concentric or eccentric. And then
Mhm.
passive tension is more like sometimes just called these passive tissues or these. I guess I would say connective tissues, but then I guess titin, the protein within a sarcomere, is not actually a connective tissue. But It's more these
Yeah. So classically, I think people assumed that all passive tension came from connective tissue. Now we know that not to be the case. Like,
yeah.
if anything, tighten seems to be responsible for more of the active or more of the passive tension than the actual
Oh.
connective tissue is. But yeah, I mean, I don't. If you chalked it all up to connective tissue functionally, like unless you're a researcher in the area, I don't know that it actually matters.
Right.
like
Right.
like
That makes a lot of sense.
that would be an incorrect belief without any like functional consequence for holding it. So whatever.
Thanks for clarifying that. And then there's something called the length tension relationship,
Yeah.
which I think kind of tells us about sort of the difference between or the relationship between active and passive tension.
Mhm.
Could you describe that for us?
Sure. So let's see. There are two components to a length tension relationship, and I will start with the active component. So
Hmm.
going back to the analogy of a bunch of little hands on a rope, um, the when sarcomeres are at a length where the maximum number of myosin heads can grab onto actin, it's creating the maximum number of cross bridges. That you can't create more active tension than that. So at the
Hmm.
sarcomere length and extrapolate it up to a whole muscle, the muscle length at which you can create the most cross bridges, that will be where you can create the most active tension. As muscles get shorter and shorter, um, some of the myosin heads will basically reach like the end of the sarcomere, so
Mm.
they're no longer grabbing onto that rope, and they're also just kind of like jamming up the works a little bit. Like they are kind of like actively pressing against the end of the sarcomere, which like resists further contraction a little bit. But yeah, biggest thing is fewer hands on the rope. You can't contract with quite as much force anymore. Same thing as the muscles get longer. Like the part of the myosin where the hands are is a finite length, and as the two ends of the sarcomere get further and further apart, there again are just like fewer hands on the actin. Um, you don't form as many cross bridges. You can't create as much active tension. So
And the place where there's the most overlap is usually mid. I feel like I've seen it. Sometimes they say it's at like your resting length. Sometimes they say it's like mid range of motion. Sometimes they say it's slightly greater than resting length.
yeah, so y- yes, that
I've
is
always been confused by this. So
that is simultaneously true and misleading. Um, so yeah, like what is termed like resting length for a sarcomere may not necessarily coincide with what we would think of as the resting
Oh.
length for a muscle.
Huh.
Um, I'll get into that in a little bit, I think.
cool.
Okay.
Um, but yeah. So basically, like it's not exactly this, but this is close enough. You can think of the active length tension relationship as basically an upside down parabola, where kind of at the middle of the length tension relationship, uh, tension is as high as it can get, and then
Active
when
tension.
yeah, active tension is as high as it can get. And then as the sarcomeres and therefore the muscles get shorter, active tension drops off. And as they get longer, it also drops off. Like the drop off is a little bit steeper on the shortening side and a
Hmm.
little bit more gradual on the lengthening side. But if you think about it like an inverse parabola, you'll be close enough. With passive tension, on the other hand, it's like roughly exponential, where
Hmm.
as as sarcomere length and therefore muscle length gets longer and longer and longer, passive tension increases more and more and more. Um, and it is as high as it can possibly be right before a catastrophic injury. Um, like,
Because you've like pulled so far, or it's been pulled so far.
yeah, like if if you stretched a muscle to the point that you just had like a full thickness tear of the muscle belly or like a full tendon rupture, right before that occurred, that would be peak passive tension. Um, and so yeah, like it's low when muscles are near resting length, and then as they get stretched more and more and more, it goes higher and higher and higher. The length tension relationship for a muscle is basically the sum of those two things. Um,
Right.
and
Active and
so
passive.
yeah, and so through just sort of like the ranges of motion where most muscles would go through most of the time in day-to-day activities, um, peak tension is going to coincide with peak active tension. Like you're getting into the realm of like pretty intense stretching before passive tension starts ramping up enough to like kind of
Mm.
overtake active tension, but you can get there. Like once again, if you just did like the hardest maximum voluntary isometric contraction of your hamstrings possible at the optimal length for active tension development, and then you also measured tension on your hamstrings with your muscle completely relaxed, no active tension, but just stretching it until you had a full tendon rupture. Uh, the 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 total measured tension right before that full tendon rupture, which at that point would be all passive tension, would be higher than the like peak
Ah.
active tension you could generate at shorter muscle lengths. Um, but yeah, so um, so yeah, like the total length tension relationship of a muscle looks kind of like a roller coaster of death, where at short muscle lengths, as the muscle gets longer and longer, you're going up, 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 up,
Oh,
up
yeah,
the
yeah,
active
yeah.
tension, and then you get to peak active tension, and then you start going down the roller coaster, and then uh, eventually passive tension starts ramping up. Generally, it starts ramping up before you get to the point where active tension is zero. So
Mhm.
it like if it starts at zero, maybe it goes up to 10, it goes down to like 4 or 5, and then it starts ramping up again as passive tension takes
Right.
over. And if you're on that roller coaster, eventually the muscle's going to rupture and the roller coaster car just shoots off into nowhere and everyone on it dies. Um, I don't know if that's a great analogy. I'll workshop it, but yes, that's
Right.
basically it goes up, it comes
Yeah.
part of the way down, and then it goes
It
up
goes
again.
back up.
And that's kind of the length, like the full summed active and passive length tension relationship for a muscle. Um, and so a logical follow up question, I think, is well, where does the passive tension start kicking in?
Yes.
And
'Cause yeah.
the answer is it differs muscle to muscle and person to person.
Ooh.
Um,
Okay.
So getting into, I think, kind of more of the meat of this, like we wanted to talk a little bit about kind of like long muscle length training and tension at long muscle lengths and whether that results in like more total tension and if more total tension drives hypertrophy.
Yeah.
Um, so like it in assumption baked into all of that is basically that the total length tension relationship of muscles is pretty stable and predictable and is similar between muscles and
Right.
between people, um, such that like such that like basically if you train through a full range of motion or at the longest possible muscle lengths, the total tension your muscles experience when they're at their longest length where you can kind of like still do like active resistance training exercise will be higher than the
Yeah.
tension at kind of like optimal length for active tension, and tension being the seems to be the primary driver of hypertrophy. If you can achieve greater total tension at long muscle lengths than you could at kind of like more optimal, kind of like mid range of motion lengths, that results in more tension, results in more muscle growth. Bada bing, bada boom. Nice and easy peasy.
Sense it's not going to be that simple.
It's not.
Can I just clarify a quick thing?
Yeah.
It sounds like you're talking about training at long muscle lengths. So just to be clear for our listeners, you're talking about strength training at long muscle lengths right now. Is that what we're talking? Like
Yes.
the observation that if you strength train at long muscle lengths, that is seems to create more muscle growth, right? Like seems like research
Yeah, yeah.
suggests that.
And
Okay.
and like an example of an exercise would be a Romanian deadlift,
Hmm.
Yes.
or
In which
or
you're
any other exercise
Hmm.
where you're going to, like you talked about, when you feel that stretch in your hamstring. Well, if you're holding a weight,
Yeah.
yeah, then you're
and
strengthening
Yeah.
the hamstrings at a long length, basically.
Hmm.
And
Yeah.
that seems to be good for muscle growth. And maybe there's an assumption that it has to do with what you're talking about, like that it's about the passive tension in that
Yeah.
end range.
But yeah, I'm skeptical of that explanation.
Yeah.
Primarily for the reason I just gave. Like that seems to be predicated on the assumption that basically all individuals and all muscles for all individuals have that sort of like
Right. The
predictable
same.
total length tension relationship, where total tension is higher at long muscle lengths than it would be at kind of like middle range of motion type muscle lengths where active tension is higher. And yeah, I mean that's just not the case. Um,
Yeah. I think that's
the
really surprising for a lot of people to hear.
the muscle lengths at which passive tension starts ramping up can vary a lot between muscles. So the muscles around the spine, like your spinal extensors, paraspinal muscles, all of that stuff, they basically seem to be strung very tight. Where even at like resting muscle lengths, they have a ton of passive tension already. Like the connective tissue and the titin just seems to be arranged in such a way that um, yeah, if you try to like flex your spine too much, you know, a bit of like you have to create a bit of active tension to resist that, but there's also just a lot of passive tension generated by those tissues to help resist spinal flexion. Um,
Yeah.
without really doing much because they do just seem to be strung very tight where there's just always a lot of passive tension. um, and then conversely your your wrist extensors seem to be strung
Hmm.
very loose, or
Oh.
your
Oh,
wrist flexors, I mean,
these ones.
seem to be strung very loose, where through like most of their active range of motion there's basically no passive tension. um,
Huh.
and that was actually discovered like almost by accident by surgeons, because like
What?
they had learned that like if you if you either need to like do surgery that involves like cutting a tendon, or if there's like a complete muscle tear or tendon rupture for one of the wrist flexors, like what they had learned is that you can determine the length at which the muscle should be when you reattach it by basically looking to see where passive tension starts ramping up. So like, you know, the
Mm.
muscle is kind of like pulled out of your forearm, and you're gonna attach it wherever, and you have like a bit of tendon to work with, and you know where you want to attach it, and you would basically just like take the muscle and start. I mean, I'm sure it's like more technical than this, but you'd basically just like pull it until you felt passive tension start going up a little bit at like a
Oh,
neutral wrist position, and then that gets to what Travis said before, like that would be what they assumed would be resting length. And the kind of assumption was that resting length is where active tension is at its peak, and
right.
also where passive tension goes from like zero to something. Like that's where, like once you get beyond resting length, that's where passive tension is supposed to start going up. Um, and that
Right.
was just kind of like the assumption. Um, so yeah, some surgeons just realize like, hey, with a lot of muscles we do surgery on, like the recovery from it seems to go pretty well. People get their function back. For wrist flexor surgery, it doesn't seem to be going that well. Like people are getting re-injured. They're having like they're feeling weakness and like functional issues. Um, and then they looked at like the wrist flexors of like people that hadn't been hurt basically,
Oh, yeah, yeah.
to see like yeah, what does the length, like, what does the passive length tension relationship in these muscles look like? And they realized, oh shit, like we've been pulling these muscles way too
Oh,
tight when we
oh no.
reattach them, because the wrist flexors, through just like normal ranges of motion, have like basically no passive tension. Um, like they're
Wow.
like the spinal erectors are strung tight,
Yeah.
where even at pretty short muscle lengths, there's still quite a bit of passive tension. The wrist flexors are strung loose, so even at
Huh.
relatively long muscle lengths, there's very, very little or basically no passive tension. Um, so
That's a
yeah, like
great example.
it's not that predictable.
Yeah, yeah.
And yeah, it varies muscle to muscle.
That makes a lot of sense and really does kind of, I guess, throw into question that kind of common explanation or assumption that seems to be out
Hmm.
there, which is that the reason that strength training at long muscle lengths produces more muscle growth is simply because total tension is higher
Hmm.
at that end range.
Yeah.
But it just seems like maybe it's not that simple, and I'm sure it's super complex. But um, thank you for explaining that. It's just always good to appreciate like how there's a lot of variability within not only in between people, but also just within the body
Hmm.
and with all these muscles.
Yeah. So,
S-
oh, go ahead.
Oh, okay. I was just going to ask. So, if that's kind of throwing a wrench into the idea that
Hmm.
strength training at longer muscle legs may not be about may not do that because of the excess passive tension. I just wonder then about stretching, because obviously
Hmm.
stretching and muscle growth is kind of like our theme today, and you've already, I think, you told us about some animal studies, and I think the implication is that it seems that maybe in humans stretching may also have the possibility to do that.
Hmm.
I guess maybe we could ask you for one. Could you tell us if that's true or not? That can happen in the human body, and then I
Hmm.
guess I'm sort of asking another question, which is just if it's true, is it because of that passive tension at end range, or could
Yep.
that be one explanation?
That is what I was setting myself up for.
Perfect.
Um, so yes, it does seem to be true.
Hmm.
Um, there is a question, however, of how relevant it is.
Uh
Um,
huh.
so, what I mean by that is there was a study, I believe from 2015, from Simpson and colleagues, that purported to show that a stretching, like a calf stretching intervention, caused some calf growth. Um,
Hmm.
and that got some people interested. I am personally um, I'm personally a bit skeptical that that study found what it claimed to find.
Mm-mm.
Mostly for like nerdy statistical reasons, but basically that study, if memory serves, it used a within subject design where one leg didn't stretch, one leg did stretch. They did like calf stretching on a leg press, where basically you'd be sitting in the leg press, one leg would be up. Um, the balls of your feet would be on the bottom of the leg press sled, and so just like the force from the leg press would stretch your calf. Um, I also think that study was controlled pretty well. I think they had like EMG electrodes on the calf muscles just to make sure that people weren't like actively contracting them, like due to
Hmm.
the just kind of like in response to the stretch, just to make sure that yeah, this is just a stretch. People aren't doing isometric contractions along with it.
It's like the
Um,
muscles relaxed, basically.
yeah, yeah. Um, so yeah, they and the stretching intervention was, I don't remember how many days per week it was, but it was like it was basically like 5 minutes at a time. So like
Hmm.
pretty long stretching. Like you're keeping one calf in a loaded stretch for 5 minutes at a time, several times a week. It was either like 3 days a week or 6 days a week, but it was like pretty consistent, pretty intense, pretty long duration stretching. And yeah, the reason why I'm like a little bit skeptical of the findings is I quibble with their statistical interpretation. Uh, Basically, what they found is that the calves weren't so like the stretched calf and the non-stretched calf weren't significantly different in muscle thickness at the start of the study. but they
Mhm.
were significantly different in muscle thickness at the end of the study.
Mhm.
Um, but like if there's, I don't know, if you could put this in the show notes,
Yeah.
um, the actual difference in thickness didn't change.
Uh?
Um,
Like
yeah,
in
like
the what?
yeah. So the stretched calf was about a millimeter thicker at the start of the study, and was about a millimeter thicker at the end of the study. Um, but like the measure itself just got like ever so slightly more homogeneous from pre-study to post-study. So like even though the like absolute magnitude of the difference didn't change, since those confidence intervals got a little bit tighter, it went from being a non-significant difference to a significant difference, even though like the actual change was pretty similar. Um,
Wow.
anyway, so a lot of people got excited about that study,
Yeah.
but I don't actually think it provided much
Mhm.
evidence for what it claimed to provide evidence for.
My
um,
gosh.
but that did not deter an enterprising researcher named Warnicki
Yeah,
um,
Warnicky.
last year, and he's done quite a few cool stretching studies. But
Mhm.
I think probably the um, like the one that like most clearly demonstrates that yeah, stretching like can like directly result in muscle growth in humans.
Mhm.
um it used a just just bonkers intervention. um so they used a calf stretching orthosis. So like if anyone listening to this has ever had like plantar fasciitis, you may have
Mhm.
been given like a device to sleep in that you like
Mm.
put your foot and calf in, strap it in, and then there's like a little mechanism that lets you pull your toes like towards your shin to just kind of like keep a stretch on your plantar fascia.
Mhm.
But yeah, like if you pull harder, you can use that to stretch your calf, basically.
Right.
Um, and so they had subjects every day for 6 weeks, if memory serves. Um, again, using a within subject unilateral design. So like each subject served as their own control. One leg stretched, the other leg didn't stretch. Um, and the stretched leg, they would pull that orthosis until the intensity of the stretch was on a 0 to 10 pain scale an 8, which honestly,
Pretty
just
high.
to throw this in here, I'm fucking skeptical of that. I think that's bullshit.
Right.
um no, like
What part is bullshit?
it wasn't a fucking 8, or they didn't like,
Can't tolerate an 8 for that long, right?
yeah, they didn't anchor the scale in their like. So an ordinal pain scale like that, here's here's how it's supposed to be anchored. And like you could trace down the like citations in the paper to like see what the paper they're cited like describes the different pain levels. But basically like 0 is nothing, like you're feeling good, like that's pretty intuitive. And then 10 should be like the greatest conceivable pain possible, like you
Right.
like like you break your femur and get your
Oh my
arm
god.
sawed off with a chainsaw. Like that's like it's
Correct.
supposed like 10 is a level of pain where like most people would just black out.
Right.
And so 8 is like
A
breaking
little
a
too
bone.
close. Yeah.
It's like breaking
Um
a bone. Right.
yeah, I mean, like an 8 fucking hurts. like
Yeah, right, right,
like a
right.
like an 8 or 9 is like getting surgery without anesthesia.
Oh
Like
my
it's
god.
it's bad.
Right.
Which one, I don't I don't think you can stretch to an 8 without just like a tendon rupture.
Oh,
like,
yeah.
I don't
Sounds like
I,
it.
I don't think that's possible to achieve. And then if it was possible to achieve, like Travis said, no, no one is willingly putting themselves in an 8 out of 10 pain situation for an hour every day. Like
For an hour every
it's
day
it's
for 6
it's not
weeks.
going to happen. Anyway, so the basic takeaway is like it was a pretty intense stretch. I think that the rating of an 8 was, as the kids would say, cap. But I mean, it was probably like a 6, which is still like pretty intense.
Yeah.
Right,
Um,
that is, yeah.
anyway, like an hour, like a straight hour of intense stretching every day with the
Mhm.
intention of, as often as possible, basically trying to get the orthosis to like the next notch, to like
Right.
stretch more and more each day. Again, for an hour a day for 6 weeks.
Yeah.
And yeah, I mean that study like pretty incontrovertibly showed like very robust muscle growth.
Mhm.
Um, like calf thickness increased by like 15% in the stretch leg versus like basically no change in the unstretched leg.
That seems like a lot.
Yeah, I mean that's considerable calf growth.
Right.
Um, and also like the study wasn't on like completely untrained people either. Like
Mm.
it wasn't on like pro bodybuilders who've tried to train their calves as much as possible, but like they used like they specifically got like a physically active cohort for the study. So
Mhm.
the not the like the type of people whose calves would be under tension from just kind of like running around, jumping, like playing sports, doing activities.
Right.
So not like completely untrained. Um, so yeah, like pretty notable effect. So I think that does pretty confidently demonstrate that
Mhm.
um, like static stretching can directly result in muscle growth.
Mhm.
Um, but like I said, I still think there's a lot of work to be done to establish the relevance
Mhm.
for a couple of reasons. One, the studies that have specifically been designed to try to observe muscle growth after static stretching interventions use calf stretching. So it's I think unlikely that whatever they're observing would only apply to the calves for just idiosyncratic reasons that only
Mhm.
apply to the calves, but
Mhm.
that is currently a possibility we can't rule out. Um,
Right.
like I'd have more confidence in it as a generalizable phenomenon if they did similar interventions for a couple different muscle groups and you saw pretty similar results in those muscle groups.
Mhm.
The other thing that makes me question the practical relevance of it is basically we have kind of shaky evidence that 5 minutes a day maybe causes muscle growth. Maybe you have some statistical interpretation issues.
Right,
Hard to
right.
say, but yeah, like 5 minutes a day, maybe a little muscle growth, but probably nothing to write home about. An hour a day of
Yeah.
very intense stretching does seem to result in muscle growth. Um, Practically, I don't know how long people want to be stretching every day. Um,
Right. Just one
so
muscle group. Like we have
right,
Yeah.
muscles all over the
Full
body.
body stretch.
yeah, there
Yeah.
there there are a lot of them. Um, so like if someone is really self-conscious about poor calf development, they've tried everything, but as we learned from The Simpsons, the calves are the hardest muscle group to add mass. Um,
I don't
I
think I know that reference, but
it was from
I mean, I know
it
The
was
Simpsons, but
it was from oh man, it was from one of the episodes where like they're teenagers, and I believe like Bart is consoling Millhouse about his shitty
ah,
calves.
his small calves.
I mean, it's like the one Simpson reference that like obliquely relates to bodybuilding in any way. So
Mhm.
every bodybuilder that's like yeah that was the age for like peak Simpsons, like anywhere from like 35 to 50, like definitely knows that reference. And like no one else because no one watches The Simpsons anymore. Uh, anyway, but yeah, so if you're someone who struggles with calf development, maybe you're
Mhm.
self-conscious about it, or maybe you just want big calves because you recognize that big calves are awesome. Um, Depending on your lifestyle, that actually might be a pretty feasible intervention. Like,
Yeah.
I know I watch an hour of TV a day.
Mhm.
And like I work online. If I really wanted to grow
Yeah.
my calves and I really thought that this was a ticket, yeah, I could just like prop my legs up in front of me either while I'm working on the computer or while I'm watching TV, get a calf stretching orthosis, get in a really deep
Mhm.
stretch, and yeah, I mean, like I could do that, but um, I don't know how many people would want to, and also, yeah, like we need to know whether it's a generalizable intervention, and
Mhm.
ideally,
Mhm.
ideally, if people would be using stretching for the purpose of hypertrophy, it would be really nice to find out that like maybe 10 minutes is enough. Or maybe like 5
Right.
minutes would be enough if it was intense enough. Like maybe the Simpson study just like didn't use an intense enough stretch. Like there are possibilities, but I think that where it's currently at, it might wind up being one of those things where it's kind of like a fun piece of trivia and like a little curiosity
Right.
where it's like, hey, did you know if you stretch enough and stretch intensely enough, it can cause muscle growth? But with the proviso that like you're never going to do it because you don't have an
Mhm.
hour a day to devote to stretching a single muscle group. But if it did come out that like, oh yeah, like 5 minutes is plenty if it's more intense, or
Mhm.
maybe like 10 minutes is fine, then it starts, and like it applies to different muscle groups, like not just the calves.
Right.
Then it would start kind of inching into the territory of maybe this is a feasible and practical intervention for, probably not to replace all of your like so-called normal training, but
Mhm. Mhm.
for instance, if someone maybe had like uh some sort of like joint issue that was like
Mhm.
exacerbated by loading but not by stretching, then
Right.
you could maybe use it as kind of like a replacement for normal training while you're rehabbing or something like that. um or if you do just have like a lagging muscle group and you don't you can only ramp training volume up but so high, and you want to maybe get
Yeah.
another little stimulus, like maybe that could be something you could play around with. So yeah, currently I think there are a lot of unresolved questions that,
Yeah.
as they're resolved, we'll either find out that this is a cool, practical, and feasible thing that probably not everyone would want to do, but that may have like tangible, beneficial real world applications. Or it might turn out that this is a fun little curiosity that no one is actually going to do because it takes so long and is so inconvenient.
That makes so much sense. Thank you for kind of putting it in perspective for us too. Like that this really has been demonstrated in research, but
Mhm,
it seems like maybe just premature at this point to
mhm.
actually begin making like proclamations that we should all start doing this and
Yeah.
this is what our stretch like what the stretching we do in yoga is going to build our muscles or something.
Mhm.
Like it seems like that's like a far ways off.
Yeah.
Um I guess oh yeah, I know what I wanted to ask you was so and I believe it doesn't seem like we really know this from research, but if it does seem that like if the stretch is long duration enough and if it's intense enough and frequent enough, it seems that muscle growth can happen. Uh
Mhm.
do you think it's because of the passive tension that we talked about? Like as you pull, then there's
Yeah.
the passive, being pulled against, and is it that or do you think it's not that? I'm sure we probably don't really know, but
Yep. I have no idea. Um, that was why I gave such a long introduction to the topic.
Mm.
Uh, just to so
To provide
yeah.
some value, because you're answering this question with no answer.
Yeah, well, no, to give context for why we don't know. Um,
Right,
so yeah,
right.
like a clear dose response relationship between tension and hypertrophy signaling like hasn't been fully established.
Mhm.
Um, And also, like, it is true that at extreme muscle links, you can generate more passive tension than you would active tension. But for just about any sort of like feasible stretch you could do,
Mhm.
um, you're not you're not going to be putting as much tension on the muscle as you would if it was like an active tension situation, like
Mm.
with calf stretching, for example. um, like if you do some calf training, like your calves can get outrageously strong. Um, like I mean, it's not uncommon. Like if someone just decided, hey, I want to get really strong calves, let's see what I can do. Like you could start doing leg press calf raises, and like just about anyone can get to the point where they can like pretty comfortably do like calf raises with like 300-400 pounds for reps. Um,
Wow.
like your calves have really great leverage. At least for
Yeah.
strength, they seem to be quite trainable. Um, and yeah, so like your calves can get very strong, but like in the context of that study, you have that calf stretching orthosis. You're manually pulling it into stretch, and so like I guarantee you the subjects in that study weren't doing like a 300 to 400 pound like row slash bicep curl to lock the stretch in. Um, like just on a practical
Right.
level, there's no way they were putting as much passive tension. Like they couldn't put as much passive tension on their calves as the active tension that the calves would be able to generate doing just about any form of resistance training.
Yeah.
Um, so yeah, like in the grand scheme of things, even if you feel a very intense stretch, unless you're stretching a muscle to the point that you're like very acutely risking a catastrophic injury, the amount of tension being generated seems to be way below what you'd experience during just about any form of like normal resistance training. We
Yeah.
don't really know if that level of tension is sufficient for muscle growth.
Yeah.
Um, and yeah, on just like the most basic level, um, we have a lot of what studies, but well, not a lot. We have a couple what studies, but we don't have why studies. So
Yeah. Yeah.
we have a couple studies looking to see, hey, can stretching cause hypertrophy? But they're not also taking like blood samples, muscle biopsies, like what you need to look at kind of like molecular markers, or like proteins and like the signaling pathways that would result in hypertrophy, to kind of triangulate a mechanism.
Yeah.
Um,
Which makes sense, right? Like if you don't know if it works the
oh
first
yeah, for
time,
sure, for
don't
sure.
waste your
Yeah,
money, but maybe in the future.
yeah, yeah. So yeah, I think of the mechanisms that are out there,
Mhm.
something tension related seems the most plausible.
Mhm.
Um, but I think that also, if that's the case, I think that has interesting implications because, like I said, the total tension your muscles would be under in those stretches would be quite a bit lower than they would generally be in just like a normal resistance training context. So
Mhm.
does that potentially suggest that our understanding of like our kind of tacit understanding of what the dose response relationship is for tension and hypertrophy might be wrong? Like maybe it doesn't
Mm.
actually take as much tension as maybe a lot of people think to cause hypertrophy,
Yeah.
or maybe it means that there's something. I was going to say something magical, but
Different.
in more, yeah, in more scientific terms, just like some mechanism that is like unique to tension at long muscle links that is not the same tension related mechanism that
Mhm.
is observed with just kind of like normal resistance training that is maybe like extra effective for muscle growth. So like one possibility there is, I mentioned the protein titin before as
Yeah.
being like a component for generating passive tension. It also has like kinase signaling regions in it, that seem to like open up and become active as the titin protein is stretched long enough under tension.
Yeah.
Um, and it's one of those things where like the like really nerd ass researchers that do a lot of like the very intense molecular stuff are kind of looking at that and licking their chops, saying, "Ooh, baby, this is a cool new little signaling protein that none of us have really looked
Right.
into yet." But there's a lot of like circumstantial reasons that we think this might actually be like pretty important and fill in a lot of gaps in our understanding of just like mechanisms of hypertrophy and kind of the signaling pathways uh, that go into all of that. So it could be that that's something that ties together the muscle growth at long muscle lengths during kind of normal resistance training and also
Mhm.
the observed hypertrophy during stretching. Like
Yeah.
it could be that there is a tension related mechanism at long muscle lengths that is not necessarily simply predicated on total muscle tension, but
Right.
is maybe based on like conformational changes of the titin protein that only occur at long muscle length, that basically like opens up a separate avenue by which you could kick off or like magnify the muscle protein synthesis initiating cascade. So who knows? Like that I think is an exciting possibility that
Yeah.
there is not currently much, if any, direct evidence for. Um, so yeah, like I don't know. All of that's like I think academic questions. I don't know
Mhm.
how you would how you would use that to actually like inform your practice.
Totally.
Other
Yeah.
than saying like, hey, like training at long muscle lengths like seems to be good. I don't necessarily know that we need to know the reason why that is, but
Yeah. Yeah.
anyway, I do think I don't know. I think a lot of people have too much of a need for closure. Like
Yeah.
they observe something, and that observation must have an explanation. Um, and you have to be confident in the explanation. And
Yeah.
I think this is one of those things where like we have observed that sufficiently intense stretching can cause muscle growth. We know that like passive tension exists, and we know that tension seems to be like a pretty important like initiator of the hypertrophy signaling cascade. Therefore, the uh, the muscle growth observed with stretching must be due to the same tension related mechanism we see with normal resistance training, and it's due to that passive tension.
Yeah.
um, and like that, I mean, that's not like a terrible line of logic to weave,
Mhm.
but the direct evidence for that being true is it doesn't exist. And I think
Right.
I think a lot of people are wanting to say, "Yep, we observe this thing, and we know precisely why it occurs, and it's this," versus saying, "Hey, we observe this thing, and here's our best tentative explanation." Um,
Right.
like, yeah, I think that it's not just enough to have a tentative explanation. I think a lot of people when they observe something, they want to feel like they know precisely why it occurred. And in this case, like we're just not there yet.
I feel like that's a really excellent answer that just really is in line with the science, and I understand and agree, and I feel like I've observed out there that it does seem just like you're saying, like there does seem to be an explanation that wants to be given that I've seen in several places where it's like it's because of this. And we know why. And it's, I don't know, more satisfying or something if you feel like you have the, you know, why it's happening. You can picture it in your mind more. But it seems to really honor the science more when we can really take a step back and admit that just we don't know yet, like it's just not known yet, and that can be okay. Like we know this effect happens, we don't know the mechanism, and that's okay.
I'd like to think so. I also feel like when I say that, I'm probably just yelling into the void. Um, I think that no, I think that and like what I'm about, this is way outside my wheelhouse, so it could be like complete bullshit. but I think that like that may just kind of be a just unchangeable part of the human condition.
Mhm.
Um, like I think that I think that like one of the deepest fears people have is like fear of the unknown. Um, like that's what just like a lot of like different fears come from. You know, from something as basic as like fear of the dark. Like, hey, I
Right.
know this space, but like I can't like I'm getting less information about it than I typically would, so I'm scared. Like I feel less secure. To like xenophobia, like the unknown people, unknown
Yeah.
cultures. Like I don't understand it as well. That like scares me a little bit. Um, like I think that like fear of the unknown is just like a defining feature of human existence, and I think that there's just like a long and storied history of people observing stuff and like needing to come up with explanations for it, um, that we like in the modern age look back on and say, well, those people were dumb as shit. Like their explanations for all of this stuff is wrong. But um, I think it's very telling that they at least took a swing, and even though they had no direct evidence for any of these explanations they put forth, they still rolled with it. Um, and yeah, I think that just on like a deep psychological level, people need to feel like they don't just understand what is happening, but why it's happening.
Mhm. Mhm.
Um, and so yeah, when we know what's before whys, I think people are just always going to jump to conclusions. Like I think people purveying information, some percentage of them will always jump to conclusions, and I think that for a large proportion of people consuming information, the ideas put forth by the people who jump to conclusions will inherently be more satisfying
Mhm. Mhm.
because they provide the at least the illusion of an explanation and a sense of closure and resolving that unknown. Um, and I think that's just how it is.
I
No
think
sense
that's
fighting it. No, I'm kidding.
yeah. No, I think that's profound, and I can relate to that myself, of course. I mean, I think, yeah, just like you said, it's maybe human nature to feel more secure when we feel like we understand and
Mhm.
like there's closure, and maybe that explains a lot about what we see out there on social media and like what gets picked up on and beliefs and information. But thank you for reflecting that. I think that's very wise. And I agree. But you're not
Don't
embodying that
don't
in what
don't
you're
think me.
telling us.
I could be totally full of shit. Um, I'm not a psychologist or anthropologist. That's
Yeah.
it's something that I've reflected on a lot because
Mhm.
it has always confused me because like I think I have a very low need for closure. Like I'm totally happy just saying like I don't fucking know why this is happening, but whatever, maybe we'll find out eventually. Um, but yeah, like I don't know, like it has always frustrated me. Like as someone who puts out content on the internet,
Mhm.
um, like this bothers me more than it should, and I hope people don't listen to this episode and then just like intentionally start doing this to troll me. But if if I if like a study comes out and it's a what study, not a why study,
Mhm.
and it is detailing something that was observed, and there's not like a obvious and clear like mechanistic explanation for it, I'll write about it and say, hey, here's what was done, here's what was observed, and yeah, like maybe this will be useful to you. Like you can use this to, affect your training, diet, whatever. Um, and then like people in the comments will jump in and be like, oh yeah, yeah, like they found this because of, and then
Oh.
just a fucking wild ass attempt to like explain the mechanism by which it happened that oftentimes is just completely implausible, but like certainly isn't supported by anything in the study. Um, and it frustrates me to no end, but it just like demonstrates a consistent pattern of people being extremely frustrated by that type of deal. Like if you just detail what was observed, but don't make like a confident statement about why it was observed,
Mhm.
it seems like a lot of people feel the need just for themselves to fill in that blank, and like
Right.
and the tone of the comments is often like, hey, like I'm doing a service to the rest of the people reading this comment section. I'm sure you also need to know why this is the case. So like I'm doing you this favor. Like this stupid author, fucking idiot, didn't even think to like explain why this was observed. So like I'll take the lead and do that. Um, and yeah, like that's something that people do all the time, and I've just been trying to figure out why. And who knows, maybe I'm being a hypocrite and I'm doing the exact same thing.
What
I'm looking for that sense of closure, like an explanation for why people are behaving that way, and no better. Who
what's
knows?
what's
This is
worse
so
though,
meta.
the authors themselves when they do the what study, then going into the discussion and give like the whole
Oh my
discussions
god,
on the
yes.
why, and then
Yes,
people assume that that's
Yeah.
that's the reason
yes,
because
that
they're not expressing enough uncertainty.
in my book, that's scientific malpractice.
Yeah.
And people will be like, well, the authors themselves say this is why they
Right.
observed it. I'm like, yeah, but they didn't collect
Right?
data on that. They had no
Right.
basis to make that claim.
Oh my
Um,
gosh.
but
Yeah.
it got through peer review, and for a lot of
I
people,
feel
it's
like
once
the
it gets through
peer
peer review,
reviewers
it's the
want
gospel truth.
I feel like the peer reviewers want to see it. They're like, but why?
I
Tell us why.
I think that's the case. Yeah, yeah.
Thank you for making that distinction. I think that'll be helpful for our audience too, just as far as like helping their own critical thinking and like as
don't
they
trust what
take
you read
in.
in the comments or in the
Yeah.
discussion.
Or even in the discussion section of an actual research paper, like
Just
just
don't read.
because yeah,
Yeah.
read but maybe with more of a critical eye. It's really helpful.
Yeah, sure. I mean that works too, I guess.
Correct. One quick thought that I had, and then I know we need to wrap up here. I don't know. Maybe you do that. I mean, I read your stuff, so I guess I don't know that I've seen this or not. But perhaps when you are writing about a research study, you could really explicitly say this was only a what study and it was not a why study, and like like maybe if you said it in bold in caps, maybe that would decrease some of those comments coming in. But maybe you feel like you already do that.
I feel like I do. I don't
Yeah.
know.
Yeah.
I mean, whatever. At this point, we've gone from talking about cool science stuff to me just complaining about people on social media. Literally the lowest form
Greg.
of content. Definitely ending this episode on a low note, and I
Oh my
take full
God.
responsibility for that.
But like I said, I think it's still helpful for us in terms of critical thinking and just learning, thinking about how we take in information and what we choose to trust and what we don't. And that's definitely something Travis and I emphasize a lot in our content is we're trying to support and encourage, more of scientific thinking and less of just like running along with those super bold, confident
Yep.
claims out there where the
Mhm.
people are like, I know this is why, and follow me because I know.
I will also say on more of a practical level, um, oftentimes like incorrect explanations are like tangibly worse and more harmful than no explanation, because the thing is like things have implications, um and so if like if for instance, uh like back in the day, people thought that like muscle soreness was caused by like lactic acid accumulation,
Oh yeah.
um
Yeah.
and there was never strong evidence for that in the first place. um but it was one of those things where it was just kind of like you observe two things together, like generally intense enough training sessions to cause muscle soreness also tended to be intense enough to increase blood lactate levels, and so bada bing, bada boom. These two things occur together, therefore one must cause the other. Which, that's not a great thought process. But that's how we wound up on the myth that lactic acid caused muscle soreness. So downstream results of that are that one, um, people for a long time just like did a bunch of stuff they didn't have to do with the assumption that, like, oh, this will flush out lactate, therefore will make me less sore, therefore I'll be able to train harder, which, like, none of it was harmful. It was mostly just kind of like active cool down stuff, which, like, is fine, but ultimately it just like wasted a lot of people's time for like several decades.
Still, I think.
Yeah. Yeah, I mean, a lot of people still do that. Yeah. Um, but it also, one, stymied research into what
Mm.
actually does cause muscle soreness,
Mm.
um, because it was thought and so universally assumed that that was a solid explanation for the phenomenon, that it was just kind of like, yeah, why look into this further? Um, and it basically took one uh, sufficiently, um, oh, what's the term? Not like curmudgeonly, but someone with like a professional degree of oppositional defiance disorder, basically, like, uh, to to look at that and be like, evidence for this seems weak. That's bullshit. Um, and the guy's name was George Brooks, and he just like completely revolutionized our understanding of lactate. Like, I mean, people used to view it as just something that was purely bad. It makes you sore. It hinders exercise performance. It's what causes the burning sensation in your muscles.
Yeah.
You want it to be as low as possible. You want to get rid of it. Like, it's just bad all around. Um, and he, for like in excess of a decade, started doing like a bunch of really just like intricate experiments to show, like, no, like, when we control all of these variables, lactate does not cause muscle soreness. Lactate does not cause the burning sensation in your muscles. Lactate does not hinder performance. In fact, it's an important metabolic intermediate to go through the Cori cycle, get recycled into ATP. It's good for performance, actually. Um, it yeah, like, yeah, basically showed that, like, everyone's assumption about
Mhm.
lactate for like literally decades was wrong. And like, no one believed him for a long time until he
What?
just did so much research that it was like completely undeniable. um and so now, like, I think he has a bit of like a professional chip on his shoulder, because he's like, hey, look, like, this was literally revolutionary stuff, and
Yeah.
I was the laughing stock of the community for like 20 years. Like, what the fuck, guys? um so it sucked for him, and yeah, it hindered the pace of
Yeah.
scientific progress, where, since people were so confident in an
Mhm.
incorrect explanation, it kept them from looking for correct explanations, and
Mm.
therefore learning new things and coming up with uh like things that would actually like help reduce muscle soreness and whatnot. So yeah, I mean, there are real costs to too confidently believing in explanations that
Mhm.
don't have sufficient evidence backing them up.
That is such an excellent example. What was that researcher's name again?
George Brooks.
George Brooks. It's very cool that he was able to, like, think in opposition to just everyone else and that he wasn't afraid to question.
Yeah, I mean, he's an absolute titan. Um,
Titan.
yes,
Yeah.
yeah, he probably like single handedly had a bigger impact on like the understanding of like exercise bioenergetics than anyone else in like the last 40 years. And even to this day, I think is still like very underappreciated.
I know it's not likely, but it would be really cool if he could somehow hear what you just said in this episode about him.
Um,
We'll send him a link.
Yeah,
maybe.
they
No,
like just
I
Maybe he
would,
something,
doesn't
I
care.
would get,
someone appreciates.
I would get shy and professionally embarrassed. Um, Also, he has a really good like advanced XPhys book. If you're ever in the market for like if you've read like a basic like undergrad XPhys text and you want to get into like the really heavy nerd shit, he has it's a dense book that's difficult to get through, but it's like eating your vegetables. Like you'll be much
Yeah,
better off for it.
it's an awesome analogy. Cool. We'll have to look that up. But Greg and Travis, I feel like we have probably come to a time to wrap up this excellent conversation. You answered all of our questions very well. Travis, did we have any lingering anything, or do you think?
No, I think we nailed it.
Yeah, I
I
do
mean, we
too.
do have to get Greg back on for the episode about sarcoplasmic
Hypertrophy.
hypertrophy. Yeah,
We would
but
love
Ooh,
that.
you know who you actually should get on for that? You know,
George Brooks.
no, I mean, like you, dude, you should get George Brooks on to talk about lactate. That would be awesome.
It's a
Um,
really good idea.
but yeah, so two suggestions for sarcoplasmic hypertrophy. Like that's a body of research that I've kept up with. But in terms of the people who've done like who have actually like conducted most of the like recent cool research in the area, either Cody Hahn
Hmm.
or Mike Roberts from Auburn.
Hmm.
Both both very cool guys, very good talkers. I think they would
Oh,
be good
good.
guests.
Thank
Not
you.
surely as loquacious as you though.
I I think at times that
TBD.
becomes a liability. Um, there's a much like the length tension relationship, the optimal level of loquaciousness.
It's an inverted U.
It's an inverse parabola, and I think I'm a bit too far on the descending limb of it.
You're going off the roller coaster.
Yeah, yeah.
Oh my gosh. Um, Greg, thank you so much for sharing so much of your knowledge today and all these explanations. I have learned a lot in this conversation, and I know that our audience will as well. We are going to put links to all of your stuff in our show notes so that our listeners can find you and follow you. But would you like what would be a place you might recommend people head to learn more from you?
Let's see. Probably strongerbyscience.com for free
Mhm.
articles. Stronger by Science podcast if you prefer the audio format. Um, if there's anything you would like to ask me directly, um, instead of DMing me, I would strongly prefer if you'd just like ask in the Stronger by Science Facebook group or subreddit.
Yes.
Because if you have a question, other people probably will as well. So answering things publicly helps cut down on like doubling up on work. And yeah, that should do it.
Yeah. This Stronger by Science Facebook page is a really awesome resource. Or the group rather. Very interactive.
It's
It is.
it's fun, man. There are some characters in there. Yeah, it's like I'd say like three quarters of the posts are good stuff with good conversations, and then like a quarter of them are I I don't know. At first, I thought it was just like a couple people who were just like kind of dumb, and it's just like how did you find this group? I'm starting. No. Like it's not as mean as it sounds.
Yeah.
Um, I At this point, I'm about 90% sure that they're like intentionally trolling, um, which is like a little polarizing. I think about half of the group dislikes it, and half of the group thinks it's very funny. And I'm the mod, and I'm in the camp that thinks it's funny. So
So you let the posts go?
yeah,
Like you let the posts.
there's about one just beautiful train wreck per week, and I enjoy that.
I want to see an example of one of those.
I'll send you some when we get done recording.
Rad. Thank you very much. That's a fun and interesting dynamic to think of in your Facebook group. I like it. Anyway, we'll put links to everything you just said and everything else in the show notes. And we highly
Mhm.
recommend following and learning from Greg. Clearly, he has so much knowledge to share. And thank you so much for sharing on this topic with us. It was awesome to have you here.
Yeah,
Thanks for
thanks
having
so
me
much,
on.
Greg.
It was a blast.